Group 5 classical control system, and then we are about to solve a question using the closed loop control system with the characteristic equation s to the power 3 plus 4.5 s to the power 2 plus 3.5 s plus 1.5 is equal to 0. And then with this, we are going to apply the Routh-Hurwitz criterion. And then this is to prevent us from solving the roots of the equation. In this video, we are going to solve the stability of the equation using the Routh-Hurwitz criterion.
So I'll be talking briefly about the Routh-Hurwitz criteria. So the Routh-Hurwitz criteria is a systematic approach which is used to determine the stability of a system. That is to determine if a system is stable, unstable, or marginally stable. So with this criteria, the main advantage of it is that it helps us to determine the stability of a system without explicitly solving for the roots of the characteristic equation, which is usually given in the question. So with the Routh-Hurwitz criteria, with the way it works using a tabular array, and this tabular array is referred to as the Routh array. So from the tabular array, after computing the elements in the array, the stability can be determined by looking at the elements in the first column of the tabular array. So the first column of the array, if the system is to be stable, then it means that the first column has positive elements. So with the Routh-Hurwitz criteria, after tabulating your elements in the tabular array, if the system is said to be stable if the first column has only positive elements or has only negative elements which are consistent. And then if there is any sign change, it means that the characteristic equation has a root in the right side of the S-plane, which proves that the system is unstable. So in summary, if your elements in the first column of the array are positive, the system is stable. If they are negative but consistent, the system is also stable. But if there is a sign change in the first column, the system is unstable because it proves that there are roots in the right side of the S-plane. And then we all know that for the general rule, for a system to be stable, it has to have negative real parts. So that is the advantage of using the Routh-Hurwitz criterion, which we are supposed to use to investigate the stability of this characteristic equation.
Okay, so I'll be talking on the concept of stability. So for stability, from the question given, we are supposed to find the stability using the Routh-Hurwitz criterion. For stability, most of the roots are supposed to be on the left-hand side for it to be stable, and when most are on the right side, it makes it unstable. So for stability, we know that with the S-plane, we have the imaginary axis, that is j omega, and we have for the real axis. So for the negative plane, we have roots being positive. Then for the positive plane, there's going to be the unstable part. So we know for the negative plane, there's going to be a growth, but for the positive plane, it's going to be unstable. So that's it. Thank you.
Okay, so I'm Christian Enchubosiako, and that's my presentation. I'll be working on the table, the Routh form table. Yes, so in forming the table, we look at the characteristics equation, and in looking at that one, we look at the powers of the S. So we have S cube, we have S square, we have S, and we have S naught. So we are going to find the coefficient of these S power values. Then we find the next, we skip one and find the next of it. So looking at the S cube, the coefficient of S cube is 1. When we skip the next power, the coefficient of that power is 3.5. Now, with the S2, the coefficient of S2 is 4.5. Skipping it, we have 1.5 as the next value. Yes. Now, for the coefficient of X, that's what you are going to find. So let's represent it by B1, and that will be 0. And for the coefficient of this one too, let's represent it by B2, because we're going to find that one too. And let's make here 0. So this is the Routh form. table.
We are going to dive into finding our B1, and from here we've already filled our table with our values that we got from here. So let's move over here. So in case you are given any equation in this form, you know that your B1 will be equal to this an minus 1 times this an minus 2 minus an times an minus 6. So let's go. So we have an minus 1 times an minus 2. This whole product, minus an times an minus 3. Now you're going to divide this whole thing by this. So we are going an minus 1. So now let's use values that we got. An minus 1 from here is 4.5. 4.5 times 3.5. Right? So minus, we have an here, 1 times 1.5. 1 times 1.5 all over an minus 1, which is 4.5. Now B1 will be equal to 4.5 times 3.5 minus 1.5 all over 4.5. So you can just punch this into your calculator and you will get 0.1667. It's always advisable to leave your answer in 4 decimal places. So this is what we get for B1. So anytime you are given an equation in this form, you can just use these parameters, these figures to just fill in your table. Then for you to be able to find B1, use this expression, then substitute to be able to get B1. Okay, so we had our B1 to be 3.167. So we are going to input that into our table. We have 3.1667. Good. So we have that in our table.
So from here, we've already calculated for B1, and then we got 3.1667. So that's for B1. So from here, we are supposed to find for C1. So we will just represent C1 here with B2. So now from here, calculating for B2, we are supposed to find the determinant for this and this minus this and this, right? So we would have 3.1667 multiplying 1.5 minus 4.5 times 0 all over 3.1667. So now we can tell from here that this would automatically go to 0. So we would have 3.1667 multiplying 1.5 minus 0 all over 3.1667. Right, so this side will go off. And we can tell from here that this 3.166 here will cancel this. So now we have our B2 here to be equal to 1.5. So now bringing our B2 here, we would get to know that our B2, which becomes the constant, to be 1.5. Thank you.
In conclusion, we see that after constructing the Routh array, that all our values in the first column are positively consistent. That is to say that there are no sign changes. And by sign changes, what I mean is we do not see a positive, negative between values, but we are seeing a consistent positive across all values in our first column. This shows us, with respect to the Routh-Hurwitz criterion, that there are 0 roots or no roots in the right side of the S-plane. In other words, this is to say that our closed loop system is stable. In other words, we can equally say that it means that because there are no values found on the right side of the S-plane, the system will not act uncontrollably. So, one advantage of the Routh-Hurwitz criterion, we see that we can calculate the stability or determine the stability of a system right from the coefficient of the equation or system given to us without calculating for the roots or values explicitly. Thank you.
get 15 points.